In this module, we shall discuss how to do substitution method in integration. That means we are going to replace a function by a single letter t and then integrate, and then after integration is completed, we replace the t back by the function. For example, I want to integrate sine cube x into cos x dx. What I do is, I have noticed that the sin x derivative is cos x. So I will start with put sin x equal to t. Now the question arises, if I am replacing a function by t, the whole function should become in t alone. If you have a part of it in t, another part in x, you cannot integrate. So we need to remove this dx, and we need to make it into dt. So for that, this is a technique we apply. We differentiate both the sides with respect to x. Then it becomes cos x equal to dt by dx. Then I cross multiply. That's why I said, if I want to replace sin x as t, its derivative cos x should be present. If suppose this cos x was not there, substitution method will not be able, you cannot apply substitution method. So the function, the integral became, instead of sin x, it is t, so it became t cube. Instead of cos x dx, it is dt, so it became t cube dt. Now integration is possible with this x raised to n formula. So t raised to 4 upon 4 plus c. So your final answer became sin raised to 4x upon 4 plus c. So what do you notice? You notice that the integral of this function is this. Let's verify if it's correct or wrong. If I differentiate sin raised to 4x upon 4, you will get 1 by 4 into derivative sin raised to 4x, 4 sin cube x into cos x. You can notice that you have got exactly the function. So this is a technique to apply. So first and foremost thing in substitution method is, whatever the term you are going to replace by a single letter t, its derivative should be present, otherwise this function cannot be integrated. Further, after replacing t and dt, the function should be only in t. There should not be any x term left out there. If there is an x term left out there, then substitution method cannot be applied. Let's have a look at the next problem. Integral cosec raised to 4x into cot, let's say cosec, okay, cot x dx. Now what can we substitute over here? If I take the derivative of cosec x, the derivative of cosec x is minus cosec x cot x. So what I do is, I split this as cosec cube x into cosec x into cot x. Now I can put cosec x as t, because the derivative of cosec x is minus cosec x cot x. I'm only short of a minus sign, and I'll show you how that minus sign or a constant can always, either you can put a minus here and put a minus and bring a minus there, or you can adjust with your dt. So I'm going to differentiate, as I told you, the dx should be replaced by dt, so I differentiate both the side. So derivative of cosec x is minus cosec x cot x. I'm differentiating with respect to x, so it became dt by dx. So cosec x cot x into dx will be replaced by minus dt. So if there is an extra constant term, you can adjust with this dt and replace it. So this whole thing can be replaced by minus dt, and this can be replaced by t cube. So it became t cube into minus dt. Now the minus goes outside, integral t cube dt. So integration became minus t raised to 4 upon 4 plus c. Now t can be replaced back. So minus cosec raised to 4x upon 4 plus c becomes your answer. And you can check that if I differentiate this, I'll come back to this. So what technique I'm going to teach you in this whole substitution method is, different names I'm going to give you so that you can easily understand what to be substituted. I am going to call this type of problems as power rule. When there is a power, what to do? Whenever there is a power for a function, you check whether the base derivative is present or not. If the base derivative is present, then base should be substituted as t. And I'm going to call this as power rule. Easy to recognize. What do you have to do? Whenever you see constant as the power, check whether the base derivative is present in the function or not. Then, if the base derivative is present in the function, substitute the base as t. Base should be put as t, not sin cube t. Sin cube x is not put as t. We are putting only sin x as t, and we call this as power rule. So whenever I talk about power rule, you should check whether the base derivative is present in the function or not. When functions are given in this format, first and foremost thing is to simplify this function. So you know that e, if the base of the log and base of the e are same, there is a cancellation possible. A raised to log m to the base a is m itself. So we try to simplify using that. So we have cot x into e raised to log sine cube x to the base c into dx. Now e and log will get cancelled. Cot I'm going to write as cos x upon sin x into sine cube x into dx. So what I've done? A raised to log m to the base a is n. So e raised to log to the base c. So they both will get cancelled, become sine cube x. So I can write here as sine square x into cos x dx. Now it has become a power. When you see a power, immediately ask the question, the base derivative is present or not? Yes, the base derivative is present. So you can put sin x as t. Remember, whenever I'm putting sin x as t, this has to be removed. Dx has to be removed. I need to express them in dt. I need to express them in t. So differentiate both the side. Derivative of cos x. So derivative of sin x, cos x. Derivative of t with respect to x. So dt by dx. So I can write directly cos x dx equal to dt. So this is obtained by differentiating. Differentiating sin x, we got cos x. Differentiating t, we got dt by dx. So that I can substitute this. So if I call this as I, so now I became integral t square dt. T square, this whole thing is dt. So it became t cube by 3 plus c. That became sin cube x upon 3 plus c. So t is replaced back by sin x. If you differentiate this, you will get this as the answer, and this is nothing but this, hence the whole answer. Here we can see the power is cube, whole cube. So the power rule, if you look at it, the base is x plus log x. If you take the derivative of x plus log x, it is derivative of x plus log x is 1 plus 1 by x. Now I don't see a 1 plus 1 by x, but you can manipulate this to create a 1 plus 1 by x. So I write this as x plus log x the whole cube, because this is going to be our base and power. And this x cube plus x square upon x cube, I take it together. Now this became x plus log x the whole cube into 1 plus 1 by x. When I separate x cube upon x cube became 1, x square upon x cube became 1 by x. Now I have got the derivative. So now I am in a position to do substitution. So x plus log x equal to t. When you differentiate this, 1 plus 1 by x is dt by dx. You are differentiating with respect to x. So 1 plus 1 by x into dx can be directly replaced by dt. So my integral I became, so I is equal to integral. This whole thing became t, so t cube into dt. It became t raised to 4 upon 4 plus c. Now replace t back. What does t stands for? X plus log x. So x plus log x raised to 4 upon 4 plus c becomes your final answer. This is how you can find the integral. Let's have a look at this function. You see a root. Remember, root is nothing but root a is a raised to half. 1 by root a is a raised to minus half. So root is also a power. Root is also a power. So naturally, this comes under the category of power rule. What is the base? What is the base here? Naturally, a is called the base. A is the base. So x square plus 2x plus 2 is the base. What is the derivative of x square plus 2x? If I differentiate x square plus 2x plus 2 I'll get the answer 2x plus 2. But my term derivative is only x plus 1. If you know that, if you look at that, you see that we are in only short of a 2. So one possibility is I can divide and multiply by 2. So what I do is, anyhow, the derivative of this is present here. Hence, I put x square plus 2x plus 2 as t. So I differentiate both the sides with respect to x. It became dt by dx. So 2x plus 2 became dt by dx. I take a 2 common. X plus 1 into dx became dt. But I don't have 2 here. If I'm short of a constant, remove that constant with the, take that constant with the dt. So now my integral became, numerator became dt by 2, denominator became root t, which I can take it as 1 by 2 into 1 by root t dt. Either you can write as t raised to minus half and integrate, or you may apply directly the formula 1 upon root x, derivative is 2 root x, integral is 2 root x. You can apply this way, or you can apply this way. T raised to minus half dt is half into t raised to half upon half plus c. Anyhow will do. This way also is fine. This way is also fine. Now you can replace t by, t is what? X square plus 2x plus 2. So root of x square plus 2x plus 2 plus c. So it's very important that every time when you decide the power rule, base derivative is present or not, you have to check. This is done mentally. Whatever I wrote here is mental calculation, which you may not write it in the solution by just looking at it. 2x plus 2, 2 common, so derivative again. Now you can do the substitution. This is how you have to think and solve the problem. Derivative of cot x is cosec square x. So how will we do? There is no cosec square x here. What I do is, I divide numerator and denominator by sine square x. Because you know 1 upon sine square x is cosec square x. So I can write this as root of cot x divided by sine square x whole divided by sin x into cos x upon sine square x. So this became integral root of cot x into cosec square x divided by cot x. If this would have not turned to cot x, then this method would have failed. Derivative has come, both are in cot, so you can simplify this. So I can write this as cosec square x divided by root cot x. So you should always check. Suppose this had turned to be some sin x, then there is no simplification possible between the two. Then this method fails. So do not think that whenever I do not have the derivative, I can always divide and multiply. That's not a correct idea. This could be done because when you divide and multiply, they both get combined. If they are not getting combined to a single term, it is not possible for you to apply this method. So every time this manipulation mentally has to be worked out, aisa ho sakta hai ki nahi ho sakta hai. If it is possible, then only you need to do it. So I'll put cot x as t. Now derivative of cot x is minus cosec square x is dt by dx. So cosec square x dx equal to minus dt. So you can write this integral as minus dt upon root t. That became minus outside integral 1 by root t dt. Either t raised to minus half, or you can write as 2 root t plus c. So minus 2 root cosec x plus c becomes your answer. Remember one thing, whenever you have a function upon, when there's a root here, directly you can apply 2 root t. I'll just show you this. This is one of the tricks that you can apply directly. It is not necessary all the time you need to put the substitution. Suppose I have a function f dash x and have a square root of f of x. That means whatever inside the root, function's derivative is present, then I can directly write this answer 2 root fx plus c. For example, I have, let's say, 1 upon x root log x plus c. Log x. This is a function. This you can apply as 1 by x root log x. Now, derivative of whatever inside the root is present, directly I can write 2 root log x plus c. This is the right direct method you can apply. Actually, it is like this. Log x is put as t, 1 by x dx became dt, answer became 2 root t, and t is replaced by log x and you got the answer. But this is another way of remembering the formula. You know that f dash x upon f of x. F dash x upon f of x. That means there is no root. This one's formula we already learned. Log of modulus fx plus c. So whenever you have a function and directly its derivative in the numerator, log of the denominator. Now we have a function with a square root. If the function with square root is there, it is like dt upon root t. So 2 root t becomes your answer. This also can be applied any function with power. You may not apply every time the substitution method, but it works with substitution method. The answer to this will be, just mentally let's calculate it. Answer to this. Suppose I put the function as t here and this will become dt. So it becomes t raised to n. Integral of t raised to n is t raised to n plus 1 upon n plus 1 plus c. So you can directly use this formula. For example, let's say I have integral of x square upon, 2x upon 1 plus x square. Let's have 2x upon root of 1 plus x square. And let's have 2x upon 1 plus x square the whole square dx. All of them are of different categories of this problem. Here directly derivative of denominator is numerator, so log of 1 plus x square. Here derivatives has a root here, function has a root here, so it comes this category, so 2 root 1 plus x square. This is of this category, so I can imagine this to be 1 plus x square raised to minus 2 into 2x dx. So a function raised to n into its derivative. Directly I can write the answer as increase the power by 1, divide by the power plus c. This way also we can directly do the problem. Now let's compare. There is some doubt all the time you will be asking you. Initially I told you if it is 3x plus 5 raised to 7, you can directly write the answer 3x plus 5 raised to 8 upon 8 into 3 plus c. Now the question arises, if it is 3x square plus 5 raised to 7, in that case, can you apply this formula? We said that if the base is anything else than ax plus b, you cannot apply the formula. However, if you have one more extra term, what is that extra term? The derivative of this. You have 6x dx with it. Then you can apply the formula. Then directly you can write 3x square plus 5 raised to 8 upon 8 plus c. Which means any of the integral formula that we have learned, if the derivative of the base is present, you can increase the power and divide by the power and write your answer directly. But we avoid using this directly because you are likely to make mistake. So we always put this as t, this as dt, and then do the problem. However, if you are confident that you will not make a mistake, you may go ahead directly by using this formula. So basically, I can say now there are total 3 formulae we learned. These 3 formulae can be applied both the ways, directly as well as the substitution method. The first formula actually is a function raised to n into f dash x dx. It is similar to x raised to n dx. X derivative is dx. You can think like that. So f of x derivative is present here. So you can directly increase the power and divide by the power and write the answer. If you have f dash x upon root fx dx, directly you can write 2 root fx plus c, because integral of 1 by root x dx is 2 root x. Here will be x raised to n plus 1 upon n plus 1 plus c. Only thing, the derivative of x should be present there, then you can apply the formula. Same way, you had f dash x upon f of x dx. That is log of modulus f of x plus c. This from where do you get? You know that dx upon x or 1 upon x dx, x derivative is dx, then log of modulus x plus c. This we had learned. So x can be replaced by any of the function you feel like. Only thing, dx will become its derivative will be present. Then only you can directly apply this formula. If I want to calculate, let's say, sec square x upon tan x dx. So this is like x, this is like its dx. So I can directly write log of modulus tan x plus c. Suppose if there is a root here, then my answer will change to 2 root tan x plus c. Suppose I have a power here, let's say tan x raised to 7 was tan raised to 7x. My answer would become tan x raised to, now the power is minus 7 plus 1 divided by minus 7 plus 1. So it became tan x raised to minus 6 upon minus 6 plus c. This is how you can modify these 3 types of function in 3 different ways, but this method can be only applied when the base derivative are present. Otherwise, this method cannot be applied. Slightly difficult problem here. First and foremost, when you see an integral function, the basic ideas which I've told you in the beginning, you should always keep. Here angle is x, here angle is x plus a, and x is the variable, dx means x is the variable, a is a constant, and I've told you before, if the angles are different, manipulation cannot be done. So we need to make all the angles same. So naturally, you know the method to do that. We need to expand this sin x plus a. So I will be writing this as root of sin cube x sin x cos a plus cos x sin a. I'm not worried about this cos a. After all, they are constants. But I'm worried about what should I do with this. I notice that this power is odd. If I take one sin x with it to become even, and I can bring it to the, I can remove the square root there. So I am going to take a sin x common. So sin raised to 4x. When I take a sin x common, this becomes cos a. What about this? There is no sin x here. How will you do it? So I'll have to divide by sin x. Now that became cot x, and this became sin square x. So I can write now this as sin square x, the root and sin raised to 4x gone. Inside the bracket I have cos a, which is like a number constant. We don't have to bother about that. This became cot x into sin a. Now you can see cot x derivative is cos x square, that is present here. 1 by sin square x is cos x square x. So I can write this as cos x square x divided by root of cos a plus cot x into sin a. Now we can think about integrating using f dash x upon root fx. I can think about integral f dash x upon root fx. I may apply this directly, or I can put this as t and this as dt. Both the methods you can apply, whichever you feel convenient. That's a choice to you. But I do not have the whole derivative. Derivative of cos a is 0 because you are differentiating with respect to the derivative will be, this is 0, this sin a comes outside, and derivative of cot x is minus cos x square x. Which means the derivative of this only I am missing with a constant, minus sin a is missing. So I can either divide and multiply with minus sin a, Once I divide and multiply with the constant, remember, sin A is not variable, x is the variable here. Sin A is a number, so number can be divided and multiplied. Now this is exactly this formula, root of fx and f dash x in the numerator. So my answer became 2 root cos A plus cot x into sin A plus c. So final answer will be minus 2 root of cos A plus cot x sin A upon sin A plus c. Some important aspects to look at this function is like this. You have which term is having the power. Here we have root of a cube. What do you mean by root of a cube? It means a raised to 3 by 2. So the tan of x square's power can be taken as minus 3 by 2. Why minus 3 by 2? Because in the denominator, when you take it in the numerator, it will be of this kind. And then you can visualize sec square of x square and x. You can visualize this function in this manner. So it is of the form a function to the power n, and then this probably will be the derivative. Or you may have to adjust it to derivative. Whenever a function has a power and the derivative of the base is present, so what should I do? What should I substitute? I should substitute the base as t. So my substitution in this problem is tan of x square should be put as t, because tan of x square is having a power and the derivative of tan is present here. So we can easily do the substitution method. So when you differentiate tan of x square, it will be sec square of x square into derivative of x square. So that becomes 2x equal to dt by dx. So I differentiated both sides with respect to x. Now I have x sec square of x square dx, but I don't have 2. So sec square of x square into x dx equal to dt by 2. So I can replace this whole numerator can be replaced by dt by 2, and this can be replaced by t. So my integral will become, so I equal to integral 1 upon root of t cube tan of x square is put as t into dt by 2. So this is how you need to always handle with a term with a power. That's why we call it as power rule. Power rule means a term having the power and the derivative of the term is present, then whatever the base, that should be put as the substitution, that is to be put as a single variable t. Now I can integrate this as t raised to minus 3 by 2, 1 by 2 goes outside into dt. Further on integration, the power is increased. So half into t raised to minus 3 by 2 plus 1. Minus 3 by 2 plus 1 will give you minus 1 by 2 divided by minus 1 by 2 plus c. This 2 and this 2 can be cancelled. So minus 1 upon root t plus c. T raised to half is root of t. T raised to minus half is 1 upon root of t. So my final answer, root of t is tan of x square. Tan of x square plus c becomes your final answer. This is how you find the integral of this function. Always you have to look at which term is having the power and the derivative of the base, is it present or not. This is the key for any power rule problem. Whenever you have a power, you check whether the derivative is present. If the derivative is not present, you cannot apply this method. In this problem, we don't see any power at all. None of the term is having whole raised to 2 whole square, nothing is there. So, but now we have to look at which term. Suppose I give you like this, a function and its derivative alone. So you cannot see the function's power. Actually, the function's power is 1. So if the function's power is 1, you cannot expect a term having power n. So you need to check only which term's derivative is present. So you can see here tan inverse of x cube. If I differentiate tan inverse of x cube, what will be my answer? 1 upon 1 plus x cube the whole square into derivative of x cube. So my answer would be 1 upon 1 plus x raised to 6 into 3x square. Check whether do you have these terms here. 1 plus x raised to 6, x square is the numerator. Only what we don't have 3, that if a constant is in, we are short of a constant, we can always adjust it. So, since tan inverse of x cube's derivative is present, I will put tan inverse of x cube as t. So, whenever here, you cannot search for the power to do the problem. You have to check which terms derivative is present. So, when you differentiate this, as I showed you here, it will be 1 upon 1 plus x raised to 6 into 3x square equal to dt by dx. Now the term 3 is not present here, so we'll adjust with the dt. So I can write x square upon 1 plus x raised to 6 dx is dt upon 3. So whenever we have a constant extra, we bring it with the dt. You can also divide and multiply with 3, that's also fine, there's no problem in that. So I will be integral. So this became t, so we write that function, we write first. Remaining whatever we have, remaining whatever the terms we have, it is nothing but dt by 3. So dt by 3. So we can write 1 by 3 integral t dt. That is 1 by 3 t square by 2 plus c. That is t square upon 6 plus c. And final answer will be tan inverse of x cube, the whole square by 6 plus c becomes your final answer. This is how you can integrate. So whenever function's power is 1, it's little difficult to understand what is the power and what is the base. So in that such case, check which terms derivative is present. Here is a slightly complicated function. We can see here integral of root of cos cube x upon sin raised to 11x, all under the root it is. So we can't see the derivative. So what we'll do is, the odd power is cos cube. So I will write it this way. Cos cube x upon sin cube x into 1 upon sin raised to 8x. 8 plus 3 is 11. Now I can write this as sin upon cos is cot. Cos upon sin is cot. So cot cube x, and if I take the square root of this, it will become 1 upon sin raised to 4x. How 4 has come? Root of 8, power 8 to become 4. So raised to half it is. This raised to half, so it became 4. This became root of cot cube x into cosec raised to 4x dx. So why did I write it cosec? Because I saw cot x derivative is present. So my strategy was like this. I wanted an even power here. Why I need an even power? Then only the square root can be taken. Second thing, I saw that cube and square root cannot be cancelled. That means the function's power should be 3 by 2. So the possibility that the function's power should be 3 by 2, because there is no question of cancelling both. So what I did, I wrote it as sin cube x so that I can combine them, and this becomes 1 upon sin raised to 8 became sin raised to 4, became cosec raised to 4. Now I am very happy because cot x derivative is cosec square, but I have raised to 4. So I'm going to split it. I can write this as cot 3 by 2x. Root is half, so 3 by 2, into cosec square x into cosec square x dx. So this is the derivative of cot x. So this, if I put cot x as t, I can adjust this in terms of dt. So if I change this also to cot, then my problem will be solved. Cot raised to 3 by 2 into 1 plus cot square x. You know that cosec square x is 1 plus cot square x into cosec square x dx. So this problem is slightly different problem compared to what we did before. So I will put cot x as t here because cot x derivative is present here. So cosec square x dx with a negative sign, or cosec square x equal to dt by dx, or cosec square x dx can be replaced by minus dt. So I can write the integral. So I is equal to integral cot x is t raised to 3 by 2 into 1 plus t square into minus dt. This way you can split it. Now open the bracket. Minus, I'll take it outside. T raised to 3 by 2 plus t raised to 3 by 2 plus 2. 3 by 2 plus 2 will give you 7 by 2. 4 plus 3 is 7 by 2 into dt. Now I can integrate that. Minus, increase the power by 1. T raised to 5 by 2 upon 5 by 2. Increase the power by 1. T raised to 9 by 2 upon 9 by 2 plus c. Now what we can do? We can replace t by cot x. So cot raised to 5 by 2x minus 2 by 9. Cot raised to 9 by 2x plus c. This becomes your final answer. This is how you can easily integrate. So tan x. So you then need to simply or modify this such a way a function and its derivative comes. So every time manipulation has been taught in different form, such a way that you can arrange them as a function and its derivative. Now we shall look at a different kind of function where we have e to the power f of x into f dash x dx. What does this mean? Function e is having a power. This power's derivative is present. All the problem with constant as base and the power with a function of x, you will always notice that the derivative of this function will be present. In such case, the power should be put as t. The power should be put as t. This is what you have to remember. And all the functions with exponential kind, this will be always like this. Whatever the power need to be put as t. So it is almost a standard method of doing the problem. So you don't have to break your head. Whenever e or a number base is a constant, the power should be put as t, and it is almost everywhere the same method. Whatever the complication, you can always start thinking of putting the power as t. So let's do this problem. Integral e raised to sin x cos x into sin 2x dx. Cos 2x dx. So naturally I need to put the power as t. So when you put the power as t, put sin x into cos x as t. Automatically you will notice that the derivative of sin x cos x is cos 2x. So let's differentiate it. Sin x into derivative of cos x plus cos x into derivative of sin x equal to dt by dx, which I can write as cos square x minus sin square x into dx equal to dt. So from this I can say that cos square x minus sin square x is nothing but cos 2x. So cos 2x dx equal to dt. So the function can be replaced now as I is equal to integral e raised to t into dt, whose integral is e raised to t itself. So your answer became e raised to t is sin x cos x, sin x into cos x plus c. So this I did a very simple problem so that you can easily understand the concept here. So whenever a function is having a power, a base is a constant and power is a function. Base is a constant, power is a function. Always power has to be put as t and its derivative will be present. Otherwise, if the derivative is not present, it will not be integrable. So you need to have the derivative to be present. So all the questions that is given to you, you will notice that indirectly or directly the derivative will be present. So the function's power should be put as t in this problem. We'll discuss one or two more problems of this kind. Not much to think about it. Exponential function. Exponential function's power is a function in x. So naturally, you will have to put this as t without thinking much. Without looking at the derivative, you can decide the power should be put as t. So what is our method? We will start with x plus tan inverse x equal to t. I am very confident that this got to be the derivative of it, because otherwise this is not integrable. So I am going to differentiate it. 1 plus 1 upon 1 plus x square equal to dt by dx. I differentiated with respect to x. When you take the LCM, 1 plus x square plus 1 upon 1 plus x square into dx equal to dt. So I can say x square plus 2 upon x square plus 1. X square plus 2 upon x square plus 1 into dx became dt. As I told you before, if base is a constant and power is a function of x, you got to put the power as t. There is no other option for you. Hence, we put x plus tan inverse x as t. This is how you recognize. So, your integral I will become a to the power t. You must have always noticed that the function after substitution, I put that as the first term, and the remaining term will be the dt. Remaining term will become dt. X square plus 2 upon x plus 1 into dx became dt. Now I can integrate this a raised to t upon log a plus c. Don't get confused here. Derivative of a raised to x is a raised to x into log a, whereas derivative integral of a raised to t is a raised to t divided by log a. So t is replaced back. So a raised to x plus tan inverse x upon log a plus c. So whenever exponential functions are present, if the power is a function of x, the power should be put as t, and the automatically derivative will be present. If the derivative is not present, the function will not be integrable. Now the next kind of problem, I'm going to call them as bad angle. Just to recognize, I've given a name for it. So like previously I told you, when a function is having a power, what to do. Then I told exponential functions, power is there, what to do. Now I'm going to teach you when the angle is bad. What is good angle and bad angle? If I want to integrate sine 4x dx, I can integrate directly minus cos 4x upon 4 plus c, because the angle is good. So which we can apply. That means if the angle is linear, direct formula can be applied. So all the linear angle I'm going to call it as good angle. What is bad angle? Let's imagine I want to integrate sine of log x upon x dx. Now I cannot directly apply the formula because the angle is bad. Here the angle is bad. What does that bad angle means? If the angle part of sine, cos, tan, etc. is other than a linear term we can directly, if the angle is ax plus b, it is a good angle. Why it is a good angle? Because we can directly integrate them. But any other function comes, sine of f of x, cos of f of x, like this, the angle part is other than the linear, then your method is put the angle part as t. You are making it linear in fact by putting log x as t. So you need to recognize this very easily. Whenever the angle part is not linear, you cannot integrate directly. In that case, put the angle part as t. Put the angle part as t. Now differentiate it. 1 by x is dt by dx. So what I can write? 1 by x dx equal to dt. So what I can write the integral as? If this is I, so I is equal to integral sine t into dt. This became t, dx upon x became dt. Now I can integrate cos t plus c, minus cos t plus t. Now I can replace minus cos log x plus c. Now check whether this answer is correct. How do you check the answer is correct? When you differentiate this, I should come back to this. What is derivative of minus cos log x plus c? Minus cos derivative is sine of log x into derivative of log x, and that's exactly that we have here. So this is a technique to be applied in bad angle. If the angle is not linear, the angle part should be put as t. That is all we have to understand in this type of problem. What is the angle part in this particular function? The function is cos of x e raised to x. So trigonometric function is cos. The angle part is x e raised to x. And it is bad. It's a bad angle. Why it is bad angle? Because cos angle is not linear. Because it is not linear, you don't have to think anything. Just put x e raised to x as t. Automatically you will notice that its derivative is present. Two cases, you don't have to think much. One is exponential power should be put as t, and trigonometric function, the angle should be put as t. You don't have to think much about it. If the angle is linear, Then of course we have to think some other method. If the angle is not linear, you can directly decide to that to be as your substitution. So differentiate it, product rule to be applied, x into derivative of e raised to x into derivative of x is equal to dt by dx. So I take e raised to x common, x plus 1 into dx equal to dt. This is exactly that you see in the numerator. So it will be present. Every time the bad angles, angle parts derivative got to be present. So I can write this as I. So my new I will become numerator is dt upon cos square t. Cos square t. How to integrate 1 by cos square? 1 by cos square to be integrated as sec square. 1 upon cos is sec t. So sec square t, whose integral is tan t plus c. Tan can be replaced, t can be replaced by x e raised to x plus c, and that is my final answer. So this is how bad angle problems can be easily solved and easily recognized. So actually the difficulty in substitution method is what to substitute is the problem that we always face. So if you know what to substitute, the integration becomes very easy to do. One more problem on bad angle. Here the trigonometric function is tan. Tan is the trigonometric function. The angle part of tan is sine inverse x, which is a bad angle. So the angle is bad here. So whenever the angle is bad, what should I do? Put the angle part as t. So I can write put sine inverse x equal to t. Without much thinking, the derivative of sine inverse x got to be present. 1 upon root 1 minus x square equal to dt by dx. So we can see dx upon root 1 minus x square. Dx upon root 1 minus x square equal to dt. So your integral I became tan t into dt. Now what is the integral of tan? Don't say sec square. Integral of tan is log of modulus sec t plus c. So log of modulus sec of t stands for sine inverse x plus c becomes your answer. This is how you can integrate very easily. So angle part is bad, we can always integrate very simple way. Now I am going to teach you a slightly different problem. Here you can say 2x minus 1 is having power root. Whenever the function is having a root, whichever term is having complicated term, you know the derivative of that is 1, that is also present. But what about these extra term? So basically I'll tell you, now the functions will be of the kind where there is an extra term. What should be done with extra term? Whether can we integrate by substitution method in such cases? What I'm going to do is, I'm going to put 2x minus 1 as t square for my convenience. I can also put as t and do the problem, but t square will make this term an integer, so integration will be a little more easier. So secondly, some problems, when it is of this kind, it may be probably better to put t square so that integration becomes much easier to calculate. So when you put 2x minus 1 is t square, remember t will be replaced by root of 2x minus 1. Suppose the problem was 3x minus 2 raised to 2x minus 1 raised to 2 by 3. Now you can see there is a cube root involved in it. In that case, you will put 2x minus 1 as t cube. This will be an easier method to calculate the integer. Even if you put only t, the problem will work. But if you put cube, it will be easier to solve the problem. So my method for this problem will be 2x minus 1 is t square. Now I'll make x as a subject. X is t square plus 1 upon 2. Now why did I make x as a subject is two reasons. One is there are x present here. These x can be replaced by t square plus 1 by 2. Second is I need dx, so I'll differentiate this. Dx by dt I'll differentiate. So 1 by 2 into derivative of t square plus 1 will become 2t plus 0. So 2 will get cancelled. So dx can be replaced by t dt. So dx will be replaced by t dt. X will be replaced t square plus 1 by 2. And this whole thing will be replaced by t square. So my calculation will be much simpler. So my integral now became 3 into t square plus 1 by 2 minus 2 into root of t square into t dt. dx became t dt. When you expand this, 3t square plus 3 minus 2 will become minus 1 upon 2 into t square dt. Now it is possible for you to integrate the whole terms without any much difficulty. We can integrate them. So I will take 1 by 2 outside the integral, 1 by 2 outside the integral, open the bracket, 3t raised to 4 minus t square into dt. Now every term is integrable here. So 1 by 2 becomes common. 3t raised to 5 upon 5 minus t cube by 3 plus c. Now I can replace t in terms of what does t stands for? What does t stands for? I will write it as 2x minus 1 raised to half. That will be better for me. So that I can write 2x minus 1 raised to 5 by 2 minus 2x minus 1 raised to 3 by 2 upon 3 plus c. This becomes my final answer. So this is how, when there is an extra term, whatever you are substituting, substitute that also in terms of t. If it is integrable, then you can integrate. Sometimes if it's not integrable, then the method fails. So it is not guaranteed method all the time, but majority of the problem will work with this method. Here the function is having degree 1, the power is 2. Because power is an integer power, you don't have to put any t square there. Just only put x plus 1 alone as t. Now these are the extra terms. Of course, dx is same as dt here. So x cube is an extra term. So I can replace this by t minus 1. dx, if when you differentiate dx by dt, you will get 1. So dx can be replaced by dt directly. So whenever it is linear, dx can be directly replaced by dt. So now the integral I can be written as, so replace x in terms of t, so t minus 1 the whole cube divided by x plus 1 became t square into dt. Now it is very easy to integrate this, expand and separate. This we learned in the beginning. So when you expand it, a cube minus b cube, for a minus b the whole cube formula, t cube minus 3t square plus 3t minus 1 divided by t square. So term by term you can separate them. T cube by t square is t, 3t square upon t square 3, 3t upon t square 3 by t and 1 upon t square. So this is integral t dt minus 3 integral 1 dt plus 3 integral 1 by t dt and integral t raised to minus 2 dt. 1 upon t square, how to integrate this? Replace at t raised to minus t. Now integrate this. We do not write this as t raised to minus 1 because this integral is different from this one. This increase the power, divide by the power, integral of 1 t, 3 integral of 1 by t is, whose derivative is 1 by t? Log. So log t, we put a modulus, minus t raised to minus 1 upon minus 1 plus c, increase the power by 1. So t square by 2 minus 3t plus 3 log modulus of t plus 1 upon t plus c. Now wherever t is there, replace it by x plus 1. So x plus 1 the whole square by 2 minus 3 into x plus 1 plus 3 log x plus 1 plus 1 upon x plus 1 plus c becomes your final answer. This is how you can easily integrate this such function. So whenever there is a complication in the terms, express that complicated term as a single variable t. That then express all other terms in t. Check whether it is integrable. Suppose in this position it was not integrable. If we had no method to integrate, then your method would fail. So it is not a guaranteed that this method can all the time be applied. So someday it can be applied, someday it may not be. So but whenever it is a linear term in the bracket, it is almost every time we can integrate. Look at the separate one. I have one term with x power as 1 by 2, another term with x power as 1 by 3. Now such type of function, it is difficult for me to integrate. So what I do is, I look at the LCM of 1 by 2 and 1 by 3. So if I put x as t raised to 6, LCM of 2 and 3 is 6, least common multiple of 2 and 3 is 6. So I put x as t raised to 6. So if I now take the power as 1 by 2, it becomes t cube. And this will become t square. So I will be able to do the problem. So let's have a look at it. So here put x equal to t raised to 6. So dx became 6 t raised to 5 into dt. I've directly done dx by dt, I cross multiply dt now. So I can replace this as I is equal to integral 6 t raised to 5 dt divided by root of t raised to 6 plus cube root of t raised to 6, which I can write as 6 t raised to 5 upon t cube plus t square. Now what I can do next step? 6 of course goes outside, t raised to 5, take a t square common, t plus 1 into dt. This t square and t raised to 5 can be cancelled. So t cube divided by t plus 1 into dt. This is very simple now. Previously it was very complicated function, but when you replace x as t raised to 6, you should understand how I selected the 6. It is LCM of 1 by 2 and 2 and 3, LCM of 2 and 3, so that when I replace in place of x t raised to 6 here, I get an integer. When I replace t raised to 6 over here, I get an integer. So in fact this is t raised to 6 raised to 1 by 3. So 6 and 1 by 3 got cancelled and we got t square. Now we can integrate this because degree of the numerator is greater than degree of denominator. One method is division. Otherwise you can add, subtract 1 and separate it and do it the problem. I do the most common and easy method by division. So t square is t cube plus t square. So change the sign, minus t square. So minus t. So minus t square minus t. So it become plus t plus 1. So t plus 1. So remainder minus 1. So I can write this as 6 integral t square minus t plus 1 minus 1 upon t plus 1. What did I do there? I have expressed as quotient plus remainder upon divisor. This is the method I have applied. So quotient is t square minus t plus 1, remainder is minus 1 and divisor is t plus 1. Now term by term I can integrate each one. 6 into integral t square dt minus integral t dt plus integral 1 dt minus integral 1 upon t plus 1 into dt. So your answer became 6 into t cube by 3 minus t square by 2 plus t minus log of t plus 1 plus c. Now wherever t is there, now you need to replace t by what? What should I replace t as? So t is x raised to 1 by 6. So wherever x is present, I will replace, wherever t is present, I will replace it by x raised to 1 by 6. So my answer became 6 into x raised to 3 by 6. 3 by 6 become 1 by 2. X raised to 2 by 6, that became 1 by 3. Plus x raised to 1 by 6 minus log of x raised to 1 by 6 plus 1 plus c becomes your final answer. So if the term has two radical powers, what are the radical powers here? 1 by 2 and 1 by 3. So in that case, you must put x as t raised to 6. Suppose we had only single radical power 1 by 3, then we would have taken as t cube. So depending on what is the radical power, accordingly t's power is decided. Now let's take different powers of sine and cos. Imagine I have integral of, let's say, sine raised to 5x dx. Now sine raised to 5 is an odd power. So the power is odd. So when power is odd, what to do, I'm going to teach you. When the power is odd, we can do substitution method. Because you can change this into sine raised to sine square x the whole square into sine x. and sin x derivative, cos x derivative is sin x. So this can be converted to cos. So we can write this as 1 minus cos square x the whole square. Now things are matching for me. This is a function in cos and this is a derivative of cos. So if it's a function in cos and derivative of cos is present, naturally my method is put cos x equal to t, because derivative of cos x is present here. So derivative of cos x is minus sin x is dt by dx. So I can say sin x dx can be replaced by minus dt. So my integral now became, I equal to integral of 1 minus cos square became 1 minus t square, the whole square, into minus dt. Now you can take the minus outside, 1 minus 2t square plus t raised to 4 into dt. Now you can separate and integrate. Minus integral 1 dt minus 2 integral t square dt plus integral t raised to 4 dt. When you integrate this minus t minus 2t cube by 3 plus t raised to 5 by 5 plus c. Now wherever t is there, you can replace by cos x. So cos x minus 2 cos cube x upon 3 plus cos raised to 5x upon 5 plus c. This becomes your final answer. This is how you can integrate an odd power. Let it be any odd power of cos and sine. You can integrate by this technique. In this one is odd and other is even. Then also substitution method is possible, because you can yourself understand that this can be splitted as sin square x the whole square, one side that is raised to 4, cos raised to 4x into sin x dx. Sin raised to 5 odd one is made to even and one extra. Now this is going to be the derivative part. So what should be t part? Naturally t should be cos x. That means I must express this whole thing as a function of cos x so that its derivative is present. So how will I express this as a function of cos x? Just replace 1 minus cos square x the whole square into cos raised to 4x into sin x dx. Now we have seen every term is a function of cos x, and the derivative of cos x is present here. So you will put cos x equal to t, and derivative of cos is minus sine. So sin x dx I am writing as minus dt directly. Actually minus sin x equal to dt by dx, cross multiplied and replaced. Now I can write this as 1 minus t square the whole square, t raised to 4 into minus dt. So the whole function is expressed as t's power. Now I can expand this. I cannot integrate this directly. 1 minus 2t square plus t raised to 4 into t raised to 4 minus outside into dt. Further on expanding this, t raised to minus t raised to 4 minus 2t raised to 6 plus t raised to 8 into dt. So that is minus of integral of t raised to 5 upon 5 minus 2t raised to 7 upon 7 plus t raised to 9 upon 9 plus c. Now what does t stands for? Cos x. So my answer became minus cos raised to 5x upon 5 minus 2 cos raised to 7x upon 7 plus cos raised to 9x upon 9 plus c becomes your answer. This is how, when one is odd and one is even, we can apply the method by splitting the odd one as a dt part and remaining should be the function of the derivative of that. In this case, tan and sec is both are present and the odd powers are there. So we may think of two ways. One is, you may think of derivative of tan x is sec square x. So putting tan x as t, one method you can think of. Another is derivative of sec x is sec x into tan x. You can think of this as t. So you have to do the trial and error, which will be more suitable, whether to go for tan x as a substitution or sec x as a substitution. Remember, any conversion from one trigonometric ratio to other is possible if there is only a square. So what you do is, first you make them into even powers. How do you make it into even powers? Tan square x into sec x, sec square x into sec x tan x. Now we convert them to even power. Why? Even power only we have the choice of conversion. Odd powers we don't have the choice of cover. So odd terms is taken. Now ask the question, whose derivative is sec x into tan x? Sec x derivative is sec x. My option is put sec x as t. I don't have the option of putting tan x as t because there is a sec cube here. Now, if I am planning to put sec x as t, this should be converted as a function of sec. It should be a function of sec. So we can convert tan square x into sec square x. Why should it be a function of sec? Because the derivative of sec x is present here. So I will be writing this as tan square x will be sec square x minus 1 and tan here sec square x remaining sec x. So it became a function of x. So I converted it into a function of x. Function of sec x. Then I put sec x tan x and dx. Now it is integrable. Now I can put sec x as t. Actually sec x tan x into dx equal to dt. I am not writing dt by dx and cross multiplying. Now I started writing directly. You also can directly write it. So my integral became t square minus 1 into t square into dt. Now it is perfectly integrable. So I can write this as t raised to 4 minus t square into dt, whose integral is t raised to 5 upon 5 minus t cube by 3 plus c. So my final answer will be sec raised to 5x upon 5 minus sec cube x upon 3 plus c. So whenever odd or even powers of functions of sine, cos, tan, sec, cot comes, you have to split them such a way. One part is even, which can be converted to different function. Other part is whatever the leftover, and that should be your dt part. So if this become dt part, what should be t? And convert those into this. So I have sec x tan x as the derivative. So I can put only sec x as t. If I have to put sec x as t, remaining terms should be converted to sec x. And if it is square, I can convert it. If it is odd power here, I cannot convert it. So first and foremost thing, change odd powers by splitting it so that remaining is even and this becomes the derivative. If that way it can be done, then only integral is possible in such type of problems. How do we approach this problem? First and foremost thing which I have told you is, if the angle part is different, the function cannot be manipulated. So the first and foremost thing that you need to do is make the angle part same. We have 4 theta here. We have theta here. So what I am going to do is, I'll convert this 4 theta into 2 theta. I'll convert this 2 theta into 2 theta. So that the whole function will become in the same angle. So 1 plus cos 4 theta can be written as 2 cos square 2 theta. Because 1 plus cos x is 2 cos square x by 2. So 4 theta became 2 theta. Then either I will write this as sin, cos upon sin, sin upon cos and take LCM, or even if you want you can write 1 upon tan theta. Because I have formula with 2 theta formula in terms of tan. So if I convert this, cos square 2 theta will come here. Let me combine this LCM. So when you take the LCM, tan theta will be numerator and 1 minus tan square theta will be in the denominator. The LCM that you had went to the numerator, and this 2 also is here, and I have ended up in a perfect formula. 2 tan theta upon 1 minus tan square theta. That is the formula for, it is not the formula for sin 2 theta. It is the formula for tan 2 theta. Sin 2 theta has got plus sign in the denominator. Now I can simplify this as cos square 2 theta into sin 2 theta upon cos 2 theta. So I made the angles all same. One cos got cancelled. Now I saw cos 2 theta into sin 2 theta. Now there are so many methods to do this problem. One of the easiest method is divide and multiply with 2. It became 2 sin 2 theta into cos 2 theta d theta. That became 1 by 2 into sine 4 theta. Now it is a perfect angle, good angle it is, direct integration. So 1 by 2 into, integral of sine is minus cos 4 theta divided by 4 plus c. So minus cos 4 theta upon 8 plus c. So I did not use any substitution method here. I could have done substitution method here, put cos as t, sine as minus dt. I could have done substitution, but I thought of doing it in terms of cos raised to 4. But if I want the answer in terms of, if I require the answer in terms of cos power, cos 2 theta's power, then of course I will have to put this as t, this as dt and do the problem. So depending on how I want the answer, I have to change the method. Let us go through the summary of what we have done today. First part I taught you is the power rule. In power rule, a function is having a power. It can be radical powers, root. It can be 3 by 2, minus 3 by 2. Any power, a function is having a power. Then what do you do? Check whether its base derivative is present. If the derivative of the base is present, then put the function, the base, as t. Whatever the base of this power, that is put as t. So the base is a function of x and the base derivative is present, so the base should be put as t. Here, exponential function, very easy to recognize. Always the power should be put as t, the f of x should be put as t, the power should be put as t. Here, the base is put as t, whereas here the power is put as t. In this case, base should be a constant. For example, if I see 10 raised to sine x, without much thought, I should put sine x as t, provided the derivative is present. The derivative should be present. If derivative is not present, we cannot integrate, so we don't have to think about that. Second, bad angle. Bad angle. What is bad angle? If the function has a sine, cos, tan, etc., all trigonometric ratio as linear, if you have ax plus b, it is a good angle. In a good angle, direct integration is your method. But if it is a bad angle, like log x, tan x, any function of x other than the linear term, then the bad angle should be put as t. So this is also very easy to recognize. Any trigonometric ratio with bad angle should be put as t. Then, there are many terms, but one term with either square root or another term with another type of function, a cube root or a fourth root, all this type of function, what is the technique that we use? Whatever inside the root is put as t square, then change this also in t, then dx also you change to dt and integrate. Whatever inside the function should be put as t cube, change x also in terms of t and then integrate. Whatever the inside the fourth root should be put as t raised to 4 and then change everything into t and then integrate. These are the things that we have done as a radical powers. Let me call them as radical powers. When radical powers are present, you must put the t's power matching with the radical power so that square root and square get cancelled, cube root and cube get cancelled, fourth root and fourth power gets cancelled. But if you have both, square root and cube root both present, let's say 1 upon square root of x plus 1 and cube root of x plus 1. Remember, both the base got to be same. If the base are different, of course you cannot do it at all. Then x plus 1 should be put as t raised to 6. Why t raised to 6 here? Because root means power is half, cube root means power is 3. If I take the least common multiple of 2 and 3, that is 6. So if I replace raised to half, t raised to 6 raised to half, they can be cancelled and integer power will come. Same way, if 1 by 3, integer power will come. So you must put x plus 1 as t raised to 6. So the radical power function should be done in this manner. Then we came to different powers of sine and cos. Suppose I have sine raised to nx dx or cos raised to nx dx and n should be odd. This method will work only if the power of sine and cos is odd. If it is odd, what should be done? It should be splitted as sine raised to square x the whole square into sine x. Now sine x is the derivative of cos. So you will put cos x as t. But if I want to put cos x as t, I must convert this as a function of cos, convert this into a function of cos, then put cos x as t. Same way here, you will have cos x as dt, so sin x should be put as t. So here you are putting cos x as t, here you are putting sin x as t. Then we learned one odd, one even power, sin cube x into cos raised to 4x, one odd, one even. What you should do, odd will become your dt. So sin square x, cos raised to 4x into sin x dx. The odd should become dt. So t should be cos x. So convert everything into cos, write it as 1 minus cos square x, convert everything into cos and then put cos x as t because its derivative is present. Then we came to mixed of tan raised to odd numbers, tan raised to 5x, odd. But we know tan x derivative is sec square x. Tan's even power, odd power we cannot do, even power. So even power of tan, what you should do? It should be written as tan square, let me take it as 6. So you will take a tan raised to 4x into tan square x. Every time tan square x will be converted to sec square x minus 1. Then open the bracket. Then tan raised to 4 will come. Again that tan raised to 4 should be splitted as. Again that tan raised to 4 should be splitted as. This tan raised to 4 will be splitted as tan square x into tan square x. This tan square x again sec square x minus 1. Again open the bracket. This process you have to continue till you make everything into the derivative and the function. Then we came to last one odd and one even. That is tan cube x into, let's say, sec raised to 4x dx. Sec raised to 5x. So both odd. Both should be odd in this. Then only it will work. So now don't think if it is even what to do. So there's some other method for that. So when one is odd and one is even, both are odd, you should make them to even first. Make them into even. Then you see that sec x tan x becomes extra. And this is the derivative of sec x. So convert this into sec x. So every term is converted as a function of sec. Derivative sec x is present. So you will put sec x as t. So this is how we have to every time manipulate and get the answer. This is a summary of the whole power rule. Two power rules are there. Base is a function, power is a number. Then base should be put as t. Second, base is a constant, power is a function of x. Then power should be put as t. Then bad angle. All angles are other than linear, bad angle. Then radical powers. Then odd and even powers of sine and cos. These are the things to remember in this particular module.